So, hello everyone, my name is Simone and I'm the neighborhood librarian here at Cliff Wright Library. So welcome to our Sustainability Speakers Series, and thank you again for coming out on this cold winter night. So before we begin, we are gathered today on Treaty 6 territory and the homelands of the Métis. On behalf of the Saskatoon Public Library, we pay respect to the Indigenous ancestors of this place. As an organization that played an important role in the settlement of Saskatoon, and as a key memory institution, we acknowledge our responsibility to respond in meaningful ways to the calls to action. The program tonight can only happen because of the partnership the library has with the Saskatchewan Environmental Society, who work hard to find knowledgeable speakers month after month. I invite today Carol from the Saskatchewan Environmental Society to come up and introduce tonight's speaker.
So my name is Carol, and I'm a volunteer with the Saskatchewan Environmental Society. The Environmental Society, abbreviated SES, has worked on environmental issues in the province for over 50 years. These issues include energy and climate solutions, water protection, biodiversity preservation, and reduction of toxic substances. We invite you to become a member of the Environmental Society. Our speaker this evening is Ron Steer, Dr. Ron Steer. Ron is a Distinguished Professor Emeritus in the Chemistry Department of the University of Saskatchewan. His research has been centered on the chemical and physical processes resulting from absorption of light, with applications in environmental science and engineering. Ron has been a member of the Natural Sciences and Engineering Research Council of Canada, president of the Canadian Society for Chemistry. He received a Master Teacher Award from the University of Saskatchewan and the John Polanyi Award for Excellence in Research from the Canadian Society for Chemistry. And he has a long history of participation in the Saskatoon performing arts community. In 2024, the Saskatchewan Association of Rural Municipalities, SARM, called for the Saskatchewan to, quote, remove itself from any national or international agreements that reference net zero. It seems to me that if more of us can explain the evidence for climate change, this will help develop popular support for reducing greenhouse gas emissions. The title of Ron's presentation is The Fundamental Physical Science of Global Warming in Less Than 50 Minutes.
Thank you very much, Carol, and thank you all for coming. This is not going to be a public performance of the arts. This is going to deal with the physical sciences. And I want to start, and I will start if I turn it on, with a summary of information that if you went to John Pomeroy's talk, you would have seen already. And that is the plot of the change in global average surface temperature as a function of time. Now, the reason I wanted to show you this particular view of this is that there's an awful lot of information on this. And the first thing that you can immediately realize is that there are 6 independent organizations actually doing the measurements here. The top one is British, the bottom one is European Community, the middle 3 are American and the Japanese. So international, independent, and some of them are trying to go back as far as historical references to temperature have been recorded, but you'll realize, I'm sure, that the protocol for obtaining an exact temperature, which has been affirmed as that particular temperature, really doesn't go back as far as 1850. And so in this particular sense, you can see that in the early years, they're really where you're trying to obtain the temperatures as a function of time, but from historical documents, there is a fair bit of difference and variation from one group to another. At about 1900, the scientific community started to realize that there was a need for making protocols available for scientific investigations that would involve a global application of protocol and methodology. So at about 1900, you begin to see that there's a bit better agreement among those groups that are working on this. So in here, a little bit better. And you can see that thereafter, it looks like there is a tendency for an increase. Bit of a spike here at about the time of the Second World War, but it seems to level off after that. And so the question is, what was going on? Well, I had something to say about that. In 1973, I actually did a piece for the then Saskatoon Environmental Society called Air Pollution and Introduction. This is a rather coffee-stained copy of that. Nevertheless, this is the real thing. Ancient technology, I absolutely assure you. Pamphlets were done by the Saskatoon Environmental Society on a variety of matters. Now, in 1973, we were primarily concerned about things like herbicides, pesticides, acid rain, smog, and so on. But there is a section in this text that I wrote about the unknowns of air pollution. And what I attempted to do was to raise the question of what the heck's happening here. If you were in 1973, why is the temperature not apparently going up as fast as everybody said that it should? We know that the carbon dioxide content of the atmosphere was going up. We know that carbon dioxide is a greenhouse gas and therefore traps the energy which is radiated by the Earth rather well. And so there should have been a general continuation of the increase in the temperature over time. Actual measurements at that time were not as well calibrated and not as global as they are now. But now, as a result of really global measurements using satellites where you can measure the entire surface of the Earth and get those measurements done in a continuously calibrated way, as you can see, there's really no difference, no significant difference among 6 different groups that are measuring these temperatures independently, and there is no doubt that there is an increase. The oscillations are natural phenomena. Several possible continuous explanations, including El Nino, La Nina, the variations in temperatures in the southern oceans. However, absolutely no doubt as to the nature of the increase. So, I'm here to do why and how. And I know that there are at least some people in the audience who probably know more about this than I do. Well, I see some physicists and chemists out there anyway. Anyway, some basics, common sense. The atmosphere and surface waters know no political boundaries. They mix. It takes a little longer for surface water to mix than it does for air to mix, but they mix without boundary. The Earth can freely exchange energy with the universe. Fortunately, we have our sun not too far away, not too close, providing us with incoming radiant energy, but we can radiate energy out into space because we are not contained. And from that perspective, this is really the basis of what is called a closed system in thermodynamics, because essentially all of the material part of the surface of the Earth is going to stay here for a considerable length of time. Certainly there can be chemical changes, carbon to carbon dioxide, carbon from carbohydrates and from so forth into carbon dioxide. There can be changes of the chemical composition, but essentially, for all intents and purposes, for our purposes, the amount of each element on the surface of the Earth is going to stay the same over a reasonably long period of time. There are minute exceptions. Here's the Earth's atmosphere. It, as you can see, is categorized according to its temperature and its temperature changes. In the stratosphere, we have the ozone layer, and the temperature in that layer rises simply because portions, oxygen and ozone primarily, absorb sunlight, mostly in the ultraviolet region. And of course, the density is diminishing as you go, of the air as you go up. And so the effect becomes larger and larger as the amount of the sun's radiant energy is captured, larger and larger amounts. Basic Science 2, water chemistry. For we folks who are here in the prairies, I always think it's important to point out that water is the most abundant chemical on the surface of the Earth, and 97.5% of that is salt water. Only 2.5% fresh water. 71% of the Earth's surface is water covered. And so we really ought to know quite a bit about what's happening to water if we're trying to figure out what's happening with the surface of the Earth. Surface water has a huge global heat capacity. So if you think about global warming, a lot of that heat is being absorbed by the water in the oceans, the surface of the ocean. And so the oceans are actually acting as a bit of a mitigating factor in helping to mitigate the effects of global warming. But increase the temperature of water, increase the amount of water vapor. And so water vaporization becomes more important in terms of the balance which occurs, and this has, of course, implications. Now, from a chemistry perspective, there's no such thing as pure water, and water is an excellent solvent. It dissolves all sorts of things, just about everything, and it actually has its own characteristic chemistry on the basis of how it behaves by itself in water, and it, as we say in chemistry, dissociates into hydrogen ion and hydroxide ion. And this, the amount of hydrogen ion which is present determines what we know collectively as the pH or the acidity. If you had absolutely pure water, it would have a pH of 7, completely neutral. Acidic is on the lower side of that, and alkaline is on the higher side. But remember, this is a logarithmic term, pH is. So if you change the pH by 1 unit, you change the acidity by a factor of 10. If you change the acidity by 0.1, if you change the pH by 0.1, you change the acidity by 25%. So small changes are important. Pure rainwater, because of carbon dioxide, slightly acidic. Ocean water, slightly alkaline. All right, now, in high school you've all seen this. The only thing I want to point out to you is that this is dynamic. All of the processes that go on with water globally are dynamic. And we get a little more of the ice and snow part than some people do, but nevertheless, we're all part of the water cycle. Now, basic science. Physics of energy, many different kinds of energy. Potential energy, the energy associated with, for example, gravitational position, water at the top of a hydroelectric dam, magnetic attraction and repulsion, electric charge attraction and repulsion. In particular, we're interested specifically about water. With water, what holds water molecules together in liquid water or in ice is potential energy of attraction between and among water molecules. If you are going to vaporize water, you have to provide enough energy to overcome that potential energy so that they escape the liquid or the solid form and get into the vapor phase. Kinetic energy is energy which is associated with motion. Guess what? Kinetics, motion. An elephant walking at 3 kilometers per hour has more kinetic energy than a human walking at 3 kilometers per hour, more massive. Molecules, which of course contain mass, can have kinetic energy of a variety of sorts, moving from place to place in the air, translational kinetic energy. Molecules consisting of atoms vibrate internally, so they are moving internally with respect to themselves, and of course the whole molecule can rotate. So kinetic energy, most important, or at least as more important for us, is radiant energy, the energy that we get from the sun, all the way, if you're talking about energy, all the way from gamma rays, X-rays, ultraviolet, UV visible, all the way through the infrared and out to the microwave region. All radiant energy. We'll be talking about that in detail. There's nuclear energy, which we would need to worry about if we were talking about nuclear processes, but we are not going to be talking about that. And in fact, there's no real significant cause and effect for global warming at present with respect to nuclear processes. In all non-nuclear processes, including water vaporization and condensation, energy is conserved. And that means that a higher temperature will result in more water vapor in the atmosphere and more aerosols. Condensation, which is the reverse of vaporization, means that energy is released, and that drives air convection. The result? Well, that's actually the basis of the increasing frequency and severity of storms. More energy, which has been produced as a result of warming of waters. All right. I want to talk about this in a little bit more detail. This is the spectrum of the radiant energy which arrives from our sun. And what is plotted here on the vertical axis is what's called the irradiance. That's the number of watts per square meter per nanometer, watts, power, per square meter area. So this is power per unit area. And this is for every segment of the wavelength or the energy spectrum, which is plotted on the bottom here. So the wavelength is in nanometers, meters times 10 to the minus 9. The middle of the visible region of the spectrum is about 500 nanometers. And so the plot here is the power per square meter for every nanometer along this plot. And as you can see, the peak is from our sun is in the visible region of the spectrum. On the outside of the atmosphere, which is what we see here in yellow, it's larger than that which actually arrives at sea level. Why is that? Well, part of it is because part of the light, some of the light is scattered by molecules in the atmosphere. Ozone and oxygen, but primarily ozone, is responsible for picking up the ultraviolet light, most of the near ultraviolet light, which comes from the sun. And then there are all of these little segments which seem to be picked out of this incoming spectrum. And what does that due to? That's due to the components of the atmosphere. So water, very important. We even see the beginning of carbon dioxide here. This little one here is oxygen. I spent a whole year in California looking at that one right there. That's O2 singlet delta G, for those of you who are spectroscopists, and so on. The Earth radiates also. So if we were to look at the emission spectrum from the Earth, here we have the sun. We've seen that already. But from the Earth, of course, the surface of the Earth, average temperature globally, annually, about 14 or 15 degrees centigrade on the surface. That's nowhere near as hot as the sun. Thank you very much. But as you increase the temperature, the spectrum will shift further and further toward the visible, to higher and higher energy, to shorter and shorter wavelengths. So here we are in the infrared. If you look at temperatures, lower temperatures, say 210 Kelvin, this is in Kelvin degrees, it will be shifted even further toward the infrared. As you increase the temperature, the whole spectrum is shifted further and further to shorter wavelengths, higher energies, more and more toward the visible. What is different, of course, here is that we see the components of absorption by components of the atmosphere, and you'll see the extent to which that spectrum of light which is being radiated by the Earth is actually picked up by the components of the atmosphere. Most of the energy which is radiated by the Earth is picked up by the components of the atmosphere. So, the radiation energy budget. Don't worry too much about anything other than the relative numbers. These are in percentages. So if you note the balance, you can see that the incoming light from the sun is balanced by the outgoing radiation from the Earth as a result of reflection by the clouds and by the surface, emitted by the atmosphere, emitted by clouds, emitted directly to space, and so on. It's a good thing there's a balance. If we had more energy coming in all the time, we couldn't live here. It would be too hot. If we had more energy leaving all the time than coming in and reducing all the time, we couldn't live here because it would be too cold. And so the balance is important. The balance also applies as far as the surface is concerned. And if you want to do a quick mental calculation, you can see that actually it also applies to the atmosphere. Now, the one thing that I want to point out here is that the atmosphere, again, plays such a huge role in this energy balance. And as you change the components of the atmosphere that absorb, you are going to change the point at which the balance is held. If we get more absorbed by the atmosphere, then the temperature is going to go up. Simple as that. Well, if I were introducing this to a third-year chemistry course as a set of students, I would have presented this almost first. This is the summary of everything that I've talked about at this point. So here we have the spectra of the sun, incoming, outgoing. Here are the materials that do the absorbing. There's scattering and ozone here. There's water, vapor, and carbon dioxide, and so on. What we will look at specifically now is those components of the atmosphere that are actually changing in content over the last 100 years or so. Carbon dioxide, oxygen, and ozone. Ozone is not going to change very much, but methane is changing, increasing. Oxides of nitrogen are changing, and of course, carbon dioxide is changing, now increasing. Now, interesting thing to note here is the huge contribution that water vapor makes. I mean, we don't really think about water vapor as being a greenhouse gas, but it does an awful lot of absorption and emission of radiation, and it turns out that in modeling, this is one of the things which is the most difficult for modelers to get a hold of, because you get more water vapor in the atmosphere, you have more absorption, more emission, but you also have more clouds. You have more clouds, you have more scattering. Oh, clouds absorb though. And then if we go back, you would have seen in the yellow energy balance the extent to which water vapor through clouds actually makes things difficult for modeling. In any event, the point to note here is that if you look, for example, at carbon dioxide, that's a pretty strong absorber in the infrared region of the spectrum, and it happens to fall in regions where water vapor is not absorbing. So, carbon dioxide, you get additional carbon dioxide, you get additional absorption of the emission from the Earth's surface by the atmosphere containing carbon dioxide. Same is true to a certain extent with methane. All right, now, difficult to do anything without talking about going back to high school again, the carbon cycle. This is a picture of this, in which the main things that I would like you to note are the importance of photosynthesis and carbon storage. So this is what is presented here is the fast carbon cycle, and you can see that photosynthesis and the absorption of carbon dioxide by the surface ocean, either through phytoplankton photosynthesis or simply by absorption in the water. Those are by far the most important parts of the cycle, fast cycle that we're dealing with. Now, if there's no important contribution from humans through fossil fuel burning, you'll see that the amount of carbon that is captured through photosynthesis is exactly matched by the plant respiration and by the microbial respiration that comes after the plant has died and begins to be eaten up by the bugs and so on. So again, there is a balance here which can be interrupted if you change the carbon constitution of the atmosphere. If we do look particularly at the oceans, we also have to think a little bit about what happens to the carbon which is deposited in the surface of the ocean, initially as carbon dioxide, but it can be captured in terms of carbonate, in particular calcium carbonate. We'll talk a little bit more about this a little later. But the White Cliffs of Dover, that's calcium carbonate. Okay. And we are now going to follow the carbon. Well, to the Antarctic? Really? I can tell you that this is the best historical capture of the carbon content of the atmosphere that is available to humankind. And it's available through ice cores, because the Antarctic region is huge, it's larger than Australia. It's covered with ice, and in some locations, that ice can be as thick as 3.5 kilometers. The ice will capture a little bit of the air that is present when the snow falls and the ice is formed. So over a period of time, a long period of time, you get more and more ice being built up, and you get a capture of the air which was present at the time that that ice was formed. So that's what ice cores do. What they're doing is they're digging through this so-called dome of ice. It's actually an upside dome. It's a dome that's like so from the surface. It's like a big bowl of ice. Now, why there? Because if you are drilling down, you must realize that ice actually moves. It actually deposits itself and spreads out as it more and more mass, more and more weight comes on top. And if you have a bowl, then all of the ice sort of goes out in the same direction, and you can maintain a continuous, uninterrupted time frame for the deposition of the ice, and therefore the deposition of the air that was present at the time that the ice was formed. So here, you want to spend your vacation in Antarctica. Here's the Epica Dome. This is the European ice drilling site. And they have gone down, as you can see, about 3.25 kilometers before they hit bedrock. There's the sampling head at the bottom. They're taking the ice out. This is obviously not out of that one. This is out of a much smaller core, obviously. And if you look at the ice in some magnification and color differentiation, you can see the layering. You can actually count the number of layers of snow that were deposited. As you can see, there are light bands and there are dark bands. Why? The light are summer bands. Why? Because in these areas, in the polar areas, in their summer, the sun's on all the time, and it's bleaching whatever is present. So you simply can, at least for some of the depth, just count tree rings to find out how far down you've gone. And then there are, as well, other geochemical methods for making sure that you're right, including finding dust at some levels, which can be associated with volcanic eruptions at some point in the history of that region. Okay, so you can measure the carbon dioxide content. Here is the carbon dioxide content from the Epica Dome, and it goes back to 800,000 years ago. And you can see that there are interglacial periods and there are glacial periods, and the carbon dioxide content gets to be about 300 parts per million in all of these ice cores. But look at what it is now. We'll come back to that. Right? Just to give you a bit of a sense of where we are with respect to people being around who knew something about what was going on. That's about the approximate start of Homo sapiens. And then, of course, there is a one-to-one correlation with what the temperature is. Now, I'm not going to go into how one gets the temperature. It's obtained by isotope abundance analysis. I won't go into the details of that, but you can see that there is actually, here we are presently in the interglacial period. The carbon dioxide content goes down, the temperature goes down. goes up and the temperature goes up. Now, can you tell from this what causes which? No, you can't. And it's simply because the precision with which one can measure the timelines is a bit too difficult. Nevertheless, there is certainly a correlation. And you can do the same thing with methane. Now this actually is a measure which expands the last 1,000 years or so. And here is the data that you've already seen for carbon dioxide. Here's a similar one for methane. Looks kind of similar, doesn't it? Kind of similar. But here is the last 1,000 years. And you can see that the carbon dioxide content has gone way up and the methane content has gone way up. And there's just absolutely no doubt about that. You know, we are dealing with unprecedented levels of carbon-containing compounds in the atmosphere for the last at least million years. And it turns out just about a year ago, the British Antarctic Survey reported another drilling site where they went back 1.2 million years, not 800,000. So nothing more, nothing unusual. I always like to show this because you don't usually go to Hawaii to shovel snow off your driveway, but here you do, in the Mauna Loa Observatory, which is one of the oldest atmospheric observatories, continuously measuring carbon dioxide, now methane concentrations on this Hawaii location. Here's what you get. Carbon dioxide content is a function of year from the late 1950s, which is when they started. The same thing with methane. The oscillations are simply the annual changes as a result of temperature and photosynthesis rate changes. Very straightforward. The reason I want to show this is that there is absolutely no question that the analysis which is done from the ice cores are completely consistent with what we can now measure. Because here are, in the blue line, the measurement from the Mauna Loa atmospheric measurements over the last 50 plus years. And then, of course, here are ice core samples, and you can see that there are many of them. This goes back just 1,000 years, but many of them, they all agree. But more to the point, they all agree that it's going up, and they all agree that when you actually have the measurement from the atmosphere that coincides with some of the early measurements of the surface ice in the Antarctic, they agree exactly. There is no question about whether or not the measurements made through the ice cores are correct. Okay, so historically, the most efficient, or at the time, most efficient steam engine was invented about 1760. So sort of the beginning of the Industrial Revolution really didn't get going for another 100 years or so. But you can see that that's the timeline that we're talking about. And I like this graph because it shows the global primary energy consumption from 1800, bit uncertain down here, but you can see how the generation of energy has changed from traditional biofuels through next coal, then oil, then natural gas. And at the moment, wind, solar, hydropower, and nuclear are still pretty small in terms of generating energy. Energy is needed. If you're industrializing, of course, as the population of the Earth increases, also a very big need. Okay. So, can there be any doubt about why atmospheric CO2 and methane are increasing? I don't think so. All right, now I want to go immediately to the other aspect of this, which is the water. What you see in red here is exactly what I've shown you before. This is the Mauna Loa atmospheric measurements. In green, this is the amount of carbon dioxide in surface water obtained in a station not too far away from the Mauna Loa station on land. And, no surprise at all, the pH goes down. Right? So, the more carbon dioxide you have in the water, the lower the pH. Now, you say, oh, well, it's hardly moved at all, you know, but remember, 0.1 pH units means a 25% increase in the acidity. Right? So, that is perfectly straightforward. Now, let's see some of the effects. Here is some data from the Australian government, the Bureau of Meteorology. The measurement on top is a measurement of the actual temperature in degrees centigrade at the Great Barrier Reef in March from 1900 through to the present. And at the bottom, that's the sea surface temperature, where the zero in this case is taken as the mean temperature between 1961 and 1990, so in here. And you can see that there is a definite change, going from cooler to warmer. The thing I want you to note, however, is that that change is a little bit smaller than the overall global change. Why? Because water, ocean water, has such a huge heat capacity. It absorbs an awful lot of heat. And so you don't see as big a temperature change in the surface waters as you would on the surface land, which is next to it. What does this do? Well, that has important effects on the such things as the coral reefs and mollusks. Here is a picture of what is called aragonite. This is a form of calcium carbonate. This is one that's produced by marine animals in making their shells. And over here we have a measure of the change in the aqueous or ocean solubility. The more red it gets, the more soluble this stuff is in the water. Okay? Well, there's the Great Barrier Reef. You can see that it is in an area where the change in the solubility of this stuff has increased an awful lot, and the temperature has gone up. And what is the effect? Well, it kills off the corals. And there's a very big operation going, particularly in the Australian Research Council funded researchers in Australia to understand all of the details of this. Now, the last thing that I want to do, use up my 50 minutes, I think I've got 6 minutes left, is to talk just a little bit about climate modeling. People have known for a long time, you increase the content of the carbon dioxide content of the atmosphere, carbon dioxide absorbs infrared radiation radiated by the Earth. The more carbon dioxide you have, the hotter it should get. So people have been trying for a long time to say, well, if we doubled the carbon dioxide content, what would the temperature be? And the very first, the chemists will be pleased to know, the very first published report predicting the magnitude of this was reported by a Swedish chemist, Arrhenius. Now, he was wrong. He got it it was too ambitious. It turns out to be the magnitude to be much smaller than this. But in fact, about the first calculation, a credible calculation, was made about 50 years ago, and they said that if you increase the carbon dioxide content of the atmosphere by a factor of 2, you should get about a 2-degree global temperature rise. Okay? Well, best source of information, if you are interested now in projecting what we should expect, from now until the end of this century, you would be well advised to go to the Intergovernmental Panel on Climate Change Reports. This is the body that was sent up by the World Meteorological Association in collaboration with the UN, and they do the reports, which are about every 5 or 6 years, which are intended to inform government and the rest of the world. And it's just of interest to note that people are not being paid to do this. These are volunteers. Volunteers read all of the published literature and do the reports. And they are really collaborative efforts of literally thousands of people. First report was 1990. The fifth report was the basis of the UN Paris Climate Accord in 2015. And the most recent one is the sixth report, which came out in 3 sections: Climate Change 2021, Physical Science Basis. Guess what? So that's what we're talking about. Climate change impacts and mitigation strategies. Now, John Pomeroy talked a lot about the impacts and potential mitigation strategies. So I'm not going to talk too much about that. Although I want to put the science basis for understanding what that is in context. And if you want to, you can go and get this from the web. I can tell you that it is long and it is the hardest thing that I have ever read. And I have a scientific background. But nevertheless, it is worthwhile reading. And no, I didn't read the whole thing. Okay. How do you do this? How do you do the modeling? Well, this is a pretty good representation. The surface of the Earth is divided up into segments. There's a vertical grid, and there's a horizontal and or surface grid. Sorry. What happens is that all of the processes that go on that influence global warming and climate change are hopefully put into the form of differential equations. These are rate equations in mathematics. This is just simply the time rate at which things change. So if you are thinking about the surface of the Earth, water surface, for example, there would be a grid that ended at the surface where there's air above and water below, and we're looking at how much energy comes through that segment of the grid and how much goes up, and then how much material goes left and right and up and down and so on. So there's a huge number of equations, and I'm told, although I've not seen this, that literally in the computer programs that are developed to do this, there are hundreds of thousands of lines of code. And so this is big. Now, how do they work? Well, it's always kind of guesswork. You do the best you can, and it's iterative, and you find out whether you did a little better this time than you did last time. Of course, one of the things that they do have to their advantage, the modelers do, is that they can retrocast. So they can say, all right, if we knew then what we know now, what we have said about the temperature change. So they can retrocast and see how to improve. And that is done. And you can see all of the kinds of processes that go on here. This is the slide that absolutely boggles the mind. This is the computing speed that's needed in order to do these. All right? So we start here, we're just starting with computers. And this is in so-called teraflops. So a teraflop is 1 trillion calculations or flops, floating point operations per second. And we're up to the need in the present day for 19,000 plus teraflops, trillion calculations per second. So these are pretty impressive computer models. And you can see that as time has gone on, the amount of information that goes into the model increases. All right, now I just want to finish with the following. Now we're going to talk about the projections, the predictions. Forget this, you've seen this already, but I want to focus on this plot, which is the change in the global surface temperature. This is the annual average as observed, as simulated, using both human and natural conditions. So here we started at 1850. Obviously, they are backing up and applying the calculations way back on data that are not very solid, so we don't need to worry about that too much. But do take a look at the black line here. That's the observed temperature change. You've seen that already. That was the second slide. Here is an indication of what the simulated temperature would have been if we dealt only with natural phenomena. Volcanic eruptions, yes. Solar input, and the composition of the atmosphere as it existed 150 years ago. You can see that there would be no temperature change, no significant temperature change. However, if you include the human, the anthropogenic factors here, the brown line is the calculation which has been now produced on an annual basis, annual average basis, by these calculations that we just looked at. And you can see that they have improved. They are now reproducing, on average, the exact observed. Now, you say, oh, what's going on with this? There's this lump here. Well, that was Mount Pinatubo eruption. And so that's part of the natural process. Lots of aerosol reflects sunlight, things cool down, and you can see that it was hard with the programs, with the calculations, with the modeling that they had to model that correctly at the time, but nevertheless, that was certainly indicative of the ability of these calculations and these models. And then finally, we should just look at what comes out of this report from the IPCC. Here we have observed warming, contribution to warming from the various human-caused variety, and you can see that the total human influence really accounts for all of the observed increase. This is the greenhouse gas part, and this part is the aerosol part. So aerosols, where you have more reflection in the atmosphere, that's going to actually bounce more sunlight away from the Earth. So that's a bit of a savior for us. But it's the difference between those two which actually is the net effect. And then here are all of the various parts, pieces that go into this. What causes the aerosols? Well, sulfur dioxide is one of the most important, and so on and so on. Finally, this is a table in which the various possibilities for an increase in the ability of the atmosphere to retain heat through the greenhouse gas effect, and what its effect is likely to be. And you can see that this goes from present day and so on. Now, these are so-called shared socioeconomic pathways, SSPs. Here's number one that they've looked at. And the number that follows here is what's called the radiative forcing. That is the incremental power per square meter that is essentially trapped by the human human-caused increase in carbon dioxide and methane and a little bit of nitrous oxide. So the numbers here increase. That means those are associated with the number of watts per square meter that we're getting to make that energy balance out of balance. That's the out of balance number. And if you look at the present level, it's actually in about this region. It's about 2.6 watts per square meter additional energy trapping capability of the atmosphere. And here is what that prediction, what the modeling says. Best estimate, 1.5 degrees. This is relative to 1850 to 1900 now, so this is the overall increase. That's the range. Gets worse as time goes on because carbon dioxide doesn't go away. The methane actually is eliminated more quickly than carbon dioxide, but it doesn't go away. And so if you continue pumping carbon dioxide into the atmosphere, it stays there. And even if you were to stop here, you would have to wait until you would expect toward the end of the century to have the temperature considerably higher than it is now. If the amount of greenhouse gases increase and continue to be contained within the atmosphere, then you can see that the problem it gets even worse. Well, that's exactly what John Palmer was talking about. So finally, in order to give you some important joy, whoop. No, don't tell me. I lost the slide. I had primed to give you a picture from the Antarctic of two Antarctic trekkers with their snowshoes and their backpacks, and they come up to the edge of the glacier. There's the water, and there are two penguins dressed in Hawaiian gear selling surfboards. and the comment is, Antarctic scientists misread the amount of global warming. Anyways, thank you very much.